Okay, so we have the question in front of us. How does gravity keep the things in orbit? So this is a problem that Isaac Newton took up and applied his equation of gravity to. So here's the Earth, and here is a very large fictitious mountain. Okay? And you imagine a man firing a gun from the top of the mountain, and he's really huge, and he's got a gun. All right. So, if he fires a low-velocity bullet, it will make a parabolic arc and hit the Earth. If he fires a faster bullet, make a longer arc and hit the Earth. Fires a yet faster bullet, make an arc and hit the Earth. But you can all see what's going to happen if he fires an even faster bullet and there's no air resistance. The bullet will just continue to fall around the Earth. And he's just done himself in. Okay. I didn't mean for that to happen. It's an unpredictable thing that happened. But
kind of a small trivia question.
Yes, go ahead. Speak up, nice and loud.
How much speed would that take? Like, what would you need to get something to do that, to actually go all the way around the Earth? What kind of forward speed would you need to get that?
Well, first of all, you've got to be outside of air resistance. But then the answer is, if you want to be in orbit very, very far, far, far away from the Earth, you don't have to be going that fast because the gravity is so much, the force of gravity is so small. So your orbital period, or your orbital velocity, decreases the further you get from the planet. So anyway, let's erase this poor fellow because he's done himself in. But now the bullet's in orbit. Okay, and Newton showed that indeed the moon itself is continuously falling around the Earth. And let's take a look at that. And it's the same thing we just described, but basically the moon has the direction of okay, so first of all let's draw the moon's orbit, okay? Let's draw the moon's orbit around the Earth. And let's redo this so we can see the whole kit and caboodle here, the whole system. Here's the Earth in the middle. Here's the moon, far away from the Earth. And here is the orbit of the moon around the Earth. Now, who can tell me what is the direction of motion of the moon? How would you describe, in terms of geometry, the relationship of the motion of the moon to the Earth at any given point around that circle? It's going in what direction relative to the Earth? Or to its orbit? Or to the moon's orbit? Yeah, it's not very clear. Forgive me. Maybe, yes, Andre.
Is it going tangent to...
Exactly. Yeah, that's right. It's going tangent to its orbit. So its velocity at any given instant, and this is an idea we have to start to understand, is this idea of instantaneous velocity. At any given instant, its velocity, v, is perpendicular, or it's tangent to the circle, okay, or perpendicular to the radius between the Earth and the moon. So if now the moon has got to this position over here, the direction of velocity has now changed. It's perpendicular. If it's in between here, now its velocity is kind of at some angle between those two. So at any given moment, the velocity is tangent to the orbit. Now, what direction is the force of gravity? Anybody know? Anybody have an idea? At any given point around the circle, who knows which direction the force of gravity acting on the moon would be? Michael.
Earth.
Right. To say it more succinctly, rather than meaning less succinctly, you just said one word, you just said Earth. Put it in the form of a sentence.
Right in the middle of that circle.
The force of gravity is toward the Earth. Yeah, toward the Earth. That's what I want to hear. That describes it better. The force of gravity is toward the center of the Earth. So let's draw that force at any given point. So at this, we'll call this 1, 2, 3. At this point, the force of gravity is toward the Earth that way. At this point, the force of gravity is that way. At this point, it's that way. Now, you remember from our discussion of vectors and acceleration that your velocity, your speed doesn't need to change for you to accelerate. What else can change to have so that when you accelerate? If your speed doesn't change. Yeah, your direction changes. So look at this arrow is the force of gravity. At every given instant, that force is causing the moon to get pulled toward the Earth. But it's also, let's kind of zoom in on a section here. Let's zoom in on one of these sections so we can see what I'm talking about. Let's just make a whole new page. Here we go. And now we're just zoomed in on the moon. Here's the velocity. Here's the force due to gravity. At every given instant, the force of gravity at once pulls the moon down, but the velocity pulls the moon, makes the moon continue moving over. So if you add the two vectors up, you get this location over here. And this is just another point along its orbit. Okay? So it's continuously getting, sorry, I didn't, this, wait a minute. It's continuously being at once pulled toward the Earth and continuing in the direction of motion. So what Newton figured is he saw this relationship and realized he needed a new type of math to deal with it. So he came up with calculus to mathematically analyze this. Because the problem is you have to look at the motion of that moon in an infinitesimally small amount of distance at a time and then figure out what the net result is going to look like. And that's where the calculus came in. So he used calculus, he determined the orbit of the moon, but the number he got didn't work because I believe the distance of the moon had been incorrectly observed by astronomers. So he put his result in a drawer for a long time. It must have been, I want to say 16 years or something like that. And then finally they came out with the right number and they published when he realized that he had it right. So this is the meaning of Newton's discovery of gravity and that equation, that gravitational equation. And so there were some major implications with this discovery. The first one, again, getting back to problems with Aristotle. Aristotle conceived of the universe as 4 elements. Now this might seem really tangential, but it's not. Okay? Aristotle conceived of 4 elements plus one mysterious 5th element. All right? Now the 4 elements are earth, air, fire, and what? Water. And the 5th element was the stuff you see when you look at the night sky, the stuff in outer space, which they at that time were just simply referred to as the heavens. Okay? Now, the problem is Newton just showed that things in outer space obey the same laws as things on Earth. And therefore, the fifth element, as it was known, wasn't really something different than what we have here. Okay? The fifth element was really matter. Outer space was not something, some perfect realm, some, it's not a heavenly realm. It's not perfect. It's very pretty, but it's made of the same stuff that is here on Earth. And so this was a major philosophical blow to Aristotle, and so this was something that was controversial at the time. But it was one of the important pieces of the scientific revolution, and that's how it came from Newton's gravitation equation. So we'll stop here and continue with the next lecture. And maybe Dr. Charbon will have something to share with us. Okay.